We now take a look at the second of the fundamental theorems of calculus. Remember, the first one, the first fundamental theorem of calculus, gave us a guideline as to how to algebraically evaluate a definite integral. But what if instead of a numerical value as the upper limit of integration, we had a variable x as the upper limit? We abbreviate the second fundamental theorem of calculus, similar how we did the first, and call it FTC2. If a function f is continuous on some open interval I containing a, then for all x element of I, so remember a nice mathematical notation here, the upside down a is a quantifier. It represents for all x. The Greek letter epsilon means is an element of. So really all this is telling us is that x is going to be in this open interval. What the second fundamental theorem of calculus states then is that if you do the derivative, d dx, of an integral from a to x, a being a number, x obviously being a variable, of f of t dt, all it's going to equal is f of x. Now think about what that's telling us. First of all, notice the change in variable right here. Notice it's a different variable than the variable of differentiation. And all this is saying is that when we take a derivative of an integral, now we know differentiation and integration are inverse operations of each other. We've seen that a lot lately. So really what happens is the derivative and the integral essentially cancel each other out, and all we're left with is the function evaluated at the upper limit of integration. In other words, what this is saying is that the derivative of an integral is going to yield the integrand evaluated at the upper limit of integration x. Now a couple things to notice about this. Notice the lower limit of integration must be a number. Upper limit of integration must be x, and that's plain x, not some variation of. We will come into problems in which you have functions of x. So maybe up here you'd have like an x squared or a 3x or a negative 5x, and we'll learn how to deal with that. But for our purposes, the statement of the second fundamental theorem of calculus, this upper limit of integration must be plain x. So all this is directing us is that if we have a problem such as this, our final answer is going to be the integrand function with the x substituted in place of t. And in another follow-up video, you're going to see several worked examples of this. But let me first walk you through an example of this to serve as an algebraic proof as to why this works. For our example, we're going to do the derivative of the integral from -1 to x of t squared plus 5 dt. Now notice a couple things. We do have our lower limit of integration being a number and the upper limit being x as required. Notice the variable of integration here is a t, which is different from the x. According to the first fundamental theorem of calculus, we're just going to take an antiderivative. So we're going to go ahead and do that. I'm going to leave the d dx notation out in front for now. Antiderivative of t squared is simply 1/3 t cubed. Antiderivative of 5 is 5t. And we're going to evaluate this from -1 to x. I'm going to continue to simply leave d dx out there, and I'm going to continue on and evaluate this according to the first fundamental theorem of calculus, which tells us that we want to evaluate this antiderivative at the upper limit of integration first. So if I substitute in x here, I have 1/3 x cubed. Now I need to substitute it in there, so plus 5x minus, now I need to substitute in the -1. When I do that, I have -1/3, and it's plus a -5, so I'll just write it as -5. I'm going to go ahead and just simplify this a little bit, that which I have in the square brackets. So now I've done pretty much all I can do according to the first fundamental theorem of calculus, but I still have this derivative out there to take. So I'm going to go ahead and take the derivative of the expression that I have in the square brackets, which would have been the antiderivative. Derivative of 1/3 x cubed is simply x squared derivative of 5x is 5, and the derivative of 16/3, well, that's 0. Notice what I have as my final answer. What I have here as my final answer is the same as my integrand, but in place of the t, I have an x. So when it comes to doing the second fundamental theorem of calculus problems, you essentially now have a really big shortcut. And you can skip all this work and just go right to the answer. So anytime you're doing a second fundamental theorem of calculus problem, and you need to be able to identify them, that's actually where a lot of students get stuck. These will show up for you on the non-calculator multiple choice part of the AP exam. And where students typically get them wrong is they just fail to realize this is the type of problem it is. If you notice you're doing a derivative of an integral, it is a second fundamental theorem of calculus problem. And you can shortcut it to your final answer. Your final answer is going to be the integrand, but in place of the variable of integration, you're going to have that upper limit of integration substituted in. In the example problems to follow in the next video, you're going to see some examples of this, some variations that you will see of this, including what happens when that upper limit of integration is not a plain x, but some other function or variation of it.